The half-life of Dubnium-270 is 1 hour. Right now, there are 6 grams in the Rochefort lab. How many grams were in the lab 3 hours ago? Okay, so if we understand the idea of half-life, and we want to do this question very quickly, without having to resort to not even just setting up a differential equation, but even just our knowledge of radioactive decay and what sort of solutions that leads to, we can say, here's what I would do. I'd sort of picture a little timeline. Right now, I have 6 grams. So the way the half-life works is within 1 hour, so 1 hour from now, there'll be half of the 6 grams left, so 3 grams. And so if you rewind the clock by 1 hour, you sort of, it doubles. Okay? It's doubling time almost. Okay? And so an hour ago, we must have had 12 grams because the half-life says if you have 12 grams, after an hour you'll have 6 grams. And so we can just work backwards. So there's 1 hour in the past. Go back another hour, you'll have had 24 grams. And so one final hour, because then that's in total 3 hours, we must have had, double it again, 48 grams. Okay? So if I'm in an absolute rush and I just understand the concept of half-life and I don't want to bring in my knowledge of differential equations, great, there we go, 48 grams. Let's do this one a little bit slower, or maybe a little more exactly, or, here's the thing. This question was very nice. 1 hour, 3 hours. 3 is a multiple of 1 hour. What if they had said 2.5, right? So this is a nice little trick if you're in this situation, but if the question had said 2.5 hours, well, my only knowledge is you have. You go from 12 to 6, 6 to 3 in 1 hour. I don't quite know what happens if you go back just a half an hour. Do you average these two? No. Okay? So it can be a little trickier. So let's imagine what would we do if we weren't lucky for this question. It wasn't 3 hours. Okay? Well, we can resort to setting up a differential equation, right? Dubnium-270, it's going to obey the law of universal radioactive decay. Okay? And so if you want to go back to basics, you can set up a differential equation and solve it. I'm just going to exploit the fact that I know what the solutions to the universal law of radioactive decay look like. The mass is initial mass, and then e to the kt. And k here, if you're familiar with how half-life works, k is actually negative ln 2 over the half-life. Okay? So t here is in hours. Well, k here is going to be negative ln 2 over 1 hour. So I actually get a formula here. I'm going to use my initial mass as 6 grams. So we get 6e to the minus ln 2t. Or you could say, well, that's going to be 6 and then e to the minus ln 2. Okay, well, e to the ln 2 is 2, and then 2 to the minus 1. This is actually going to be 6 over 2t, if we want to. And now we could say, okay, 3 hours ago, that's minus 3 hours, or in another, if it was another question that we were doing, minus 2.5 hours, you could say, all right, the mass 3 hours ago is 6 over 2 to the 3. Okay? To the minus 3. Yeah, I have it written right here. I don't know. I was looking at this 3 here, but 6 over 2 to the minus 3, right? Just plugging in our time here. I knew something was wrong because I was about to say, wait, hold on, it's getting smaller? No, I just said the answer is 48. So that was just me accidentally, absentmindedly forgetting my minus sign for a moment. But it's okay, we've corrected it all. So this is 6 over 1/8. And then we get, well, that's 6 times 8. And look at that, that's 48. Right? We all know 6 times 8 is 48. If you don't know it, you're not great. But there we go, 48. So we can actually use our knowledge of half-life and set up a formula. But if you really want to, you can go back to all the way to differential equations and universal law of radioactive decay. Or because we got lucky that 3 is a multiple of 1, that we're measuring in terms of whole half-lives, we can just walk it back in this case. But if it was 2.5, no, that would not be the way we would go about doing it. But either way we do it, 48 grams is the answer.